Okay, let's continue now in the third part of building the phylogeny of a protein family with the BLAST pipeline. So as I said, here we will use some commands that Iasonas wrote, and we will use Diamond instead of BLAST. Diamond actually is an accelerated BLAST. First we will build a database, and then we will search a query in this database, and then we will use some bash commands to parse the results and some scripts. Okay, so if we think about it, there are two ways that we can do the BLAST search. Let's think about it a little bit more. So we have here the human genes, so this could be a file with 13 or 12 aquaporin genes, so aquaporin 1 and so on. And here we have the chimp proteome. Which will be a very long file of, I think, about 50,000 proteins. It might be more, it might be 80,000. I don't remember how many there are here. So we can either make a database of this file and use this as a query, or make a database of this file and use this as a query. So this will be option number 1 and this will be option number 2. Now in the script that I show, this is the option number 2 has been implemented, but perhaps we can try option number 1. I think, even if I haven't tried it, the only difference will be in the e-value of the BLAST score. And I think that in this case, in the case number 1 actually, it will be, the e-value will be more accurate, because e-value denotes or is related somehow to the probability of finding a match by chance. So if we search one protein here against this one, since this is very small, the probability to find something by chance will be small. So it will be like that we will have much smaller e-values than in reality, perhaps. On the other hand, if we search one protein here, this file, then since it is much bigger, the probability to find something just by chance will be evaluated better. But we can try both of them. In the script, the option number 2 has been implemented, but now we will try option number 1. And this will be a good example actually to compare the results of the two options. Okay, so we will build a database from the chimp proteome and then from the mouse proteome, and then we will compare, we will search the human aquaporins against this database. Okay, let's go to the script to see how this works. This is, I will make immediately directly a script, a bash script, that we will put all these commands inside there, and then we will make it more beautiful. Okay, so let's go here. I will name it BLAST search.sh. So the first thing will be to make the database. Okay, let's modify it. So I wrote the script. As query, I use the file called aquaporin-human.fa. The organism will be chimp, and then I use this diamond command that calls so the diamond make database command. As input, I use the org proton.fa, so it will be here chimp proton.fa. It's this file that we generated previously when we downloaded data from Uniprot, and then this will be the database name. So if I will run only this command on line 4, then we will have a file called chimp.dmnd. DMND comes from the word diamond, just to denote here that it is a BLAST database generated by the diamond command. Okay, and then actually I run BLAST P with query, my query here, it will be the aquaporin-human fa, and then as a database I use the org DMND, so the chimp. This will be the output format. It will be the output format 6, which will put all the results in a table format, and then the output file name, I just use here the name of the query and the name of the organism, and then just these flags, ultra sensitive, to find more results, and the number of threads 8. So if you run this in a cluster, you can use something like 30, 32 or so on, 16, whatever you want. Actually, you can do something like that to find out how many threads you can run in your computer. You can run the command htop, and then you can see here, for example, that in my computer I can use up to 8 threads from 0 to 7. In your computer this might be different. Okay, so if then I want to use the same thing for mouse, I will do that here in this way. It's not optimal again. Maybe a better result would be to use external variables for that, but doesn't matter in my case here. Okay, so this will be mouse. Let's check. So it's called mouse actually, yeah, mouse proton.fa. So now the org will be mouse, the input will be mouse proton.fa. It will create the database, and then here it will write the human aquaporin.fa versus mouse .blast. Okay, I save this, I go back to terminal, and then I make this executable, plus search, and I run it. Okay, let's see how it will go. It will take some time probably. As far as I see, this number will needs to go to 64. I will pause it and I will continue later, but this is the process. Okay, everything has finished up to now, and if I will do an ls, I see the two files with the BLAST results, aquaporin-human versus chimp and aquaporin-human versus mouse. Now if I will see how these files look like, okay, so this is the human ID, this is a mouse ID here, and here are some results from the BLAST. Now the e-value threshold that I have used here, the default value is 10 to the minus 5, so here everything should be below 10 to the minus 5. So what I have done here is that I have taken each human protein and I have searched it against the the mouse database. So it is possible that one human protein matches several mouse proteins, or it's possible that several mouse proteins matches to the same ID. So the same mouse protein matches to different human IDs. So eventually what I'm going to do, since I need to get the similar genes from human to mouse, is to parse this second column and find the unique results in the second column. So how many different genes, which different genes from mouse I have that match the 13 aquaporin proteins in humans. Okay, let's see that. So here I have mouse, I have (218) lines, but not all of them are unique. I mean, not all. I have more than one time probably each mouse protein. So I will show you how to do that in the command line, but everything we will put that in a script. Okay, if I will just get the second column from this file, it will be this one, and if I will ask for the unique results, sort minus u, I will just have these 22 results. Okay, and this is what I need actually. Normally I should save this in let's say mouse.genes, but then I will get all this command and I will put it in my script. Okay, so this is my script, and here a comment get genes of interest, and I will use my file name conventions here. So this will be the query versus org. Okay, I can use this command. Okay. And here it will be org again. I can use this command here one time and here one time. Okay, now the process will be that I will do a blast and then I will parse the results, and then I will do a blast in mouse and parse the results. I can use genes here for example. Okay, and this goes away. Now I will not run this command, instead I will run it here, just not to repeat everything. So this will be mouse genes, and if instead of mouse here I will write chimp, I'll get the chimp genes. Okay, so for chimp I have 25 genes, and for mouse I have 22 genes. Okay, now the idea will be to go to the proteome and get this gene. So let's see how the proteome looks like. Now this will be, for example, mouse proteome. Okay, it looks like that. So I see the ID is here of the gene, and this is similar to the ID that I have written. So I need to find the lines that have the ID that I search for, and then get the sequence up to the point that I find the next record. So this will not be very easy to do it in Bash, just because the number of lines correspond to one protein ID is not fixed. So for example, for this protein I have, I don't know, 8 lines, and for this one I have many more. I have two options for that. One will be to convert this file to a file that will have one line per protein, so to concatenate all these lines here to one line, or use a bash, so to concatenate and then use grep to search for the pattern and get this line and the next line using the -A1 option of grep. Instead, probably I will just write a small Python script to find the pattern that I'm searching for, and then print out the lines up to the next protein. I think this is a better option because simultaneously with that I can modify the protein name to remove gaps and other special characters that phylogenetic programs like RAXML do not like later on. Okay, so let's see how to build that. I will build that and then I will explain it. Okay, I wrote a small Python script that uses some regular expressions to get the genes from the list of genes. So from this file, to get all these entries from this file. Okay, the script works like that. So the arguments are defined by the genes file and db file. Genes file is a file with the gene names, and db file is the proton. And then it uses some regular expressions to generate in the beginning a large motif with all these gene names that exist in this genes file concatenated with the OR. So for that I have to use the RE escape operator of the regular expressions, because the file names contain this OR here, so I need to escape that. Okay, I just remove the last OR that I put. I compile it. I generate a second pattern that contains the FASTA greater than, which defines the sequence name, and then I search for the first pattern, for this pattern with the the protein names within the database. Okay, so if I will run it, it will print out all the names. Also here I use some I use the split function to split the sequence name and just use the parts of the sequence that I need, because the sequence name in the original FASTA contains actually several gaps here. Okay, so these are not very good names that exist. I just use this ID, which is unique anyway, and then the first letter after the first word after the gap. Okay. So let's see how this works. Now, with this way, I get, for example, aquaporin 5, aquaporin 4, aquaporin 9, and so on. I will write this in a file. Mouse aquaporin.fa, and I will do the same for chimp, and chimp here, and chimp here. Let's check the chimp aquaporin. Okay, seems good. Okay, I will just take this command and I will put it in my script. Copy. Okay, one time here. Replace this with org. Here and org here, and one time here. Then the next thing will be to concatenate the results. Okay, so let's see. Cat human. So this is aquaporin, human fa, chimp, aquaporin.fa, and mouse aquaporin.fa in a single file. So I will call just this aquaporin. The next thing will be to align it. And I will create the aquaporin alignment. Okay, let's see how it looks like. Oh, in humans, in humans I have gaps, I don't like it. Okay, let's remove the gaps in humans. Okay, I think I wrote a small set script to do that. Let's concatenate it again. It looks better now. There is, I missed something. Okay, I missed some. Okay, I'll do that manually because it's not so large anyway now. But yeah, you should do that in a script, of course. Or maybe better to automatize it a bit more to do that in the human. Okay. Okay, so it looks, I think, better now. Yeah. Okay, let's align it. So I have to remove all the gaps from the sequence names because alignment 3 reconstruction programs do not like it. Okay, now I have the alignment, which looks like that. Yeah. So human in the beginning, and then it's chimp, and then it's mouse. Right, and now I will use RaxMLNG to build the alignment. I just run RaxMLNG without any arguments, just to show me some help here. I'll do it fast now. So I will use this command, I will modify it, and here I will use the aquaporin. So here I must do normally a model test to find out which is the best model, but I will just leave it like that now. So this is the initial number of trees that I have to use, and these are the bootstrap values, the bootstrap repetitions, so 200 repetitions here. So I will let it run. Of course, all these commands will be better to put them in the script that we have, and then boom, run the whole script as a whole. Okay, that's it for now. Thanks a lot. Oh, let's fix this problem. Okay, what is the problem here? Yeah, of course, I need to put as an input the alignment file, not the FASTA file. Yeah, and it will start. Okay, this will take some time, a couple of hours, and then we will have the results. That's all.